Hello everyone, this is Mr. 13 Things, and you really don't want to know where that came from. But what I'm going to do here in the next couple minutes is go through the setup of a problem that I'm going to lay out in the Khan Academy exercise development. I'm not going to call it an app, but a framework that would allow science teachers to, an example basically of the power of taking some of the things you're doing already, getting rid of some of the grading, and still getting at that core information that you're trying to get at people. Particularly I'm addressing probably around here 7th and 8th grade science. I do this based on personal experience with some of the incredible local science teachers at 7th and 8th grade in my local district here, and also on the fact that teaching at a technical college for years, I found myself teaching these same concepts. So they're not, some of these real important basic concepts aren't going in as much as they really should we teach them well and correctly at the beginning. And so I'm going to use this problem mostly not just to show you the framework and how it would work. And I'm going to keep, it's a basic trajectory problem, so I'm going to kind of explain it here. You have the ground here, and elevation basically is going to be a flat piece of ground, and we have, I'm going to use one color here, and we're going to shoot something up here with a velocity equal to velocity initial and an angle here equal to theta initial, if you would. And my question is how long and how far? How long will it go? And how long in time until it hits the ground? And how far? And of course, we could also go to the basic how high. Now, many of you recognize this as one of the first kinematic equation problems you see, but I'm going to approach it first and foremost, as I always do with my students, with pure logic. And that logic is going to be based on a couple of things, but one, the fact that the acceleration due to gravity is equal to 9.8 meters per second squared. This minus meaning that we're calling the y positive and the x this way is positive. So we're going to now say very quickly in the logical bit, we're going to call that it's around 10 meters per second squared, which is 10 meters per second per second. And I'm going to show you the problem as we do it anecdotally here, based on some really key numbers. And one is we're going to make this to start with the angle equal to be 30 degrees off of horizontal. And the velocity, we're going to call it 100 meters per second, right? The v initial in it. So I'm going to do this for this reason. Very quickly, for all kinds of different reasons, it's important for students to realize that if you throw something up in a triangle that's 30 degrees, that's not a great one. That if this is 100, then this here is 50. And this one is actually the square root of 3 over 2 times 50, if you want to think about it. But by throwing something up at 30 degrees, you're splitting out half of the magnitude into the up direction. So if we start this as 100 meters per second, then we know the v and the y is equal to 50 meters per second, and the v and the x is something different entirely. It's something like the square root of 3 over 2, which is 0.866 times the 100, and so it turns out to be it's 86.6, which is really tough for students to grab. Of course, you wouldn't have done this until you first taught them to throw the ball up at 50 meters per second, etc., etc. Okay, so here's the logic in this, and the logic in this is this. If something is leaving at 50 meters per second, a second later, that's its velocity vector, a second later its velocity is 40 meters per second, and then 30 meters per second, and then 20 meters per second, or 10 meters per second. So it takes 5 seconds to stop going up. And then it's going to take 5 seconds to come down. Right? So 5 seconds to go up, 5 seconds to come down, so the total time is going to be equal to 10 seconds. The velocity was 86.6. The velocity in the x direction is not changing. So it's going to go 866 meters. Again, this is assuming no air resistance. And then finally, so we have how long in time. how far, and how high is the tougher problem. But in this how high, you then get to something called averaging, and then so you know that it started, the initial equals 50 meters per second, the final equals 0 meters per second, the bar or the average is 25 meters per second. It went up for 5 seconds. If you think about that, its average was 25, and so the height, so y max, is equal to 125 meters. And so we have the how high, the how long in time, and the how far. And in this particular problem, we have taught them one that as long as you keep this to be 30 degrees, right? Because it, in fact, the sine or the opposite over the hypotenuse of 30 degrees is 1/2. As long as you've fixed it to 30 degrees, this is something that can be done mental math-wise. Now, what I'm going to do with the next bit is to lay this out with a framework where what you actually are using the kinematic equation. And this is the reason why we're doing that, is that so you can basically quantify and code in the con system so it will generate an infinite number of scenarios. So the students can step up from the one that they know into one that they can apply basically some equations to. This is advanced for 7th and 8th grade. However, the problem that stirred me to understanding it this way, which was throw something up at 50 meters per second, how long until it stops going up? It stops going up in about 5 seconds. All of this is assuming 10 meters per second. So that's the layout of this problem. What I'll do after this is lay out the framework of how it works within the con system, and then show you how you randomize and give hints and the like for something. Again, this is somewhat complex, much beyond 7th and 8th grade, but something that 7th and 8th graders would, should, and could grasp if we start pushing the trigonometry down into 5th and 6th grade. Thanks for listening.